come to Michigan, but she kindly agreed to give lectures virtually. So she'll speak now, and then she'll speak tomorrow morning. She's one of the leading cosmologists studying a connection between modified gravity and dark energy, as well as connections to the early universe. And she will tell us about modified gravity and dark energy. Tessa, I'm not sure if you were planning to post these slides to the Day 3 lectures channel. If you are open to that, maybe later you can do so. If not, that's okay.
Sure, yeah, that's fine. I can post something after the session.
After the session, and then people can also ask and answer questions there. So Tessa, off to you.
Okay, very good. And I'm going to start a timer just so my chair knows I do have a timer, so I'll see when it gets to 40 minutes. Okay, hi everyone. I'm really sorry I can't be with you there in person. I was quite ill at the weekend and I was advised not to travel, so sorry about that. But I hope you're having a great week, and we'll certainly do our best to replicate the experience for you with me online. So I'm going to be talking about modified gravity and dark energy. These are two concepts that in my mind are very, very closely related, almost synonymous, but we'll see a little bit later today what the sort of technical distinction between them is. Before we jump into the science, I thought I would tell you just a little bit about who I am and where I am. So I'm talking today from Portsmouth in the UK, where I work at the Institute of Cosmology and Gravitation. Now, probably a lot of you have not heard of Portsmouth, and that's fine. Whoops, can I advance my slides? Ooh, sorry, I did click something and a button came up saying I was muted, which would not be a particularly good start. So, this is Portsmouth in the UK. It's a relatively small city on the south coast of the UK. Everyone flies into London, of course. If you jump on a train towards the south coast, about 90 minutes, you reach us in Portsmouth. And as you can see, it's a really nice waterfront city. We've got this kind of interesting tower. It's always this sunny 365 days a year. I'm sure you can tell that's not true because it's the UK. And we happen to have at the university the Institute of Cosmology and Gravitation, or the ICG, which is one of the largest departments in cosmology in the UK. And if you can't make us out, we're actually that building just there, so about 10 minutes from the waterfront. So I say this because in the audience today, we've probably got plenty of you who are in research already, and if you are ever in the UK for research, you might want to look us up and see if we're a place you'd like to come visit. I'm aware we might also have in the audience or online people who are just finishing master's degrees and are perhaps looking to study for PhDs. So just one line on that. So the PhD application cycle in the UK kind of follows this fixed annual calendar where it opens in late November and applications close end of January. So that's the time to be looking at our website, looking for the projects that will go up and getting in contact. Okay, that's where I am. Just a little bit about me and sort of what I study. So I've got three sort of big areas of my research, which you'll hear about all three in these lectures. First of all, modified gravity theories. So I started life as a theorist, really trying to think about how do we test like the whole space of possibilities there are for dark energy and modified gravity, and what makes a good modified gravity model. And because of that, I say I speak Lagrangian. We'll see some of that later today. But then I sort of later in my career moved into trying to connect those gravity theories to large-scale structure, to actually connect theory to observables. And that often requires numerical simulations, which is a pretty sticky topic. but it also means you get involved with some of the data from the latest galaxy surveys. And then gravitational waves were this thing that kind of took over my life from 2017 onwards, when there was the binary neutron star merger GW 170817. I'll tell you tomorrow about how that helps us test ideas in modified gravity. And I now lead the kind of part of the LIGO-Virgo-CAGRA collaboration that tries to test sort of exotic ideas in cosmological gravity. So that's who I am as a scientist. However, when we've got a lot of young people together in one place, I think it is important to stress and remind everyone that you can and should, and I really hope you do, have life outside your studies and outside of science. So for me, that involves dancing salsa and also doing a lot of hiking in the UK South Downs. So these versions of me exist as well. Okay, so intro's over. Here is the plan for the lectures. So today is really going to be the sort of theory lecture. So we're going to start by looking at why we would modify gravity and meet some of the sort of key principles of how we build a modified gravity theory via something called Lovelock's theorem. And then the real meat of today is we will move through some examples of modified gravity theories. And in particular, I'll focus on 4 sort of major examples that have really shaped this field sort of historically. And then tomorrow's lecture will be a bit more on the sort of data and the connection to observables. So we'll talk about what gravitational waves tell us about modified gravity, and we'll also kind of connect to large-scale structure observations. So if today is kind of too much theory, please don't let that put you off for tomorrow, which will be more phenomenology. And so here comes the health warning. Today's slides do contain plenty of equations. However, the fiddly details of every term are not important. So you don't need to understand every factor of 2 or things like that. What I'm going to try and convey to you is the general structure of these theories, the processes by which we manipulate them, what we actually do to compute with them, and physically what is going on. And as some of you will have seen in the Slack channel already, I have shared a PDF of some lecture notes, or rather it's on my website, that has like a lot of the actual expressions written out in their full gory detail, if that's something that would help you. Okay. Final bit of preamble, because we are on YouTube, there may be typos in these slides. I once gave a talk that was broadcast on YouTube where there was a sign error in one of my equations, and you would not believe the number of people that came to the comments to point out the sign error. So there might be sign errors, there might be factors of 2, such is life. Okay. Let's get going then with, just a recap of something that I think lots of you will have touched upon at some point, which is why do we want to modify gravity in the first place? And I won't kind of go through all the sort of lore around dark energy, but I think most of you or all of you will know that we have really strong evidence in cosmology for a cosmological constant in our universe. At least we did up until very recently. For the first time in the latest results from the DESI telescope, there's some kind of interesting hints of something that's not a cosmological constant. I'm not going to talk about that today. I don't know if maybe Will mention that in his lectures on Thursday and Friday. But instead, I've got a very nice plot from one of Dragon's papers, actually, that shows the combination of constraints from supernova in blue, the cosmic microwave background in red, and baryon acoustic oscillations, so this characteristic scale in the galaxy distribution in green. And you see all of them favor this particular point in parameter space where omega m, the dark matter fraction of our universe, is decidedly less than 1. It's just below 0.3. So we've got something making up our universe that is not dark matter. And that something seems to have an equation of state W, which is consistent with -1, which would be the telltale sign of a cosmological constant. However, as is well known, this is a really, really problematic situation for our universe. So if you compute the value of the energy density in the cosmological constant that you would need to fit these observations, it's this number here in terms of electron volts, very small, 10 to the minus 11. And if you compute the value that we would expect from quantum field theory, that is the famous 10 to the power 110, right? So this is this massive discrepancy that gets talked about, that is the cosmological constant problem. And I sort of go over this to perhaps stress to people, please don't forget what a huge problem this is for lambda CDM. I'm sure some of you in the audience are working on other things, not modified gravity, doing cool bits of cosmology, and you just sort of assume lambda CDM as the starting point. And that's fine, but please don't get so used to assuming lambda CDM that you kind of forget that this problem is there hiding under the rug. And this whole endeavor in dark energy or changing the laws of gravity at least originates as an attempt to solve this problem, right? To ask, is there something we're missing here? Well, clearly there is something we're missing, but could it be that this huge discrepancy is arrived at by applying the wrong laws of gravity, the wrong physics to the largest scales of the universe? And if we have a theory of gravity that changes the largest scales of the universe, perhaps this kind of discrepancy will make sense. Now, you could well ask, why are we allowed to do this? Why are we allowed to tinker with the laws of gravity when they're really well tested in the solar system, for example, or laboratory experiments on Earth? And I have a plot here that I made about a decade ago now, Christ, that represents why we're allowed to do this. So this plot shows you a range of gravitational systems. And what it's got on the x-axis is the gravitational potential. So simplest sort of case to consider, think of a test particle outside a central mass m orbiting at a radius r. Right, and in that case, the gravitational potential is proportional to gm over r. On the y-axis, we have a different quantity which assesses the curvature of the space-time. Now, it's actually something called the Kretschmann scalar for anyone who's a GR aficionado, but for the rest of us, it doesn't really matter today, but in our simple example of a test particle, this quantity would be proportional to gm over r cubed. So this is just a scalar telling us how distorted the space-time metric is. And what you can see in this plot is a range of systems spread out over this two-dimensional parameter space. So I like to start here in the middle. I'm hoping you can see my mouse, but maybe someone can interrupt me if you can't see my mouse. Otherwise, I'll carry on assuming you can.
I can see your mouse, yes.
Good. Okay, thank you. Good. So in the middle here, these blue dots labeled SS are the planets of the solar system. And they're all lying on a straight line because they're all effectively test particles probing the same gravitational potential, which is of the sun, right? Moving up towards a slightly higher potential, slightly more highly curved regime, we hit things like pulsars, PSRs. MS is the main sequence of stars. WD is the population of white dwarfs, so more compact objects. And then right up here in the high curvature, high potential regime, we have the population of neutron stars and stellar mass black holes. And this vertical line here at a potential of 1 is effectively representing the sort of Schwarzschild radius, if you like, in the case of a black hole. So all of these things, quite high curvature. Moving down a bit, we've got these points labeled S stars. These are the stars orbiting around the central black hole of the Milky Way. Again, they're all on a straight line because they're orbiting the same central mass. And as we sort of follow down that dashed line, we get to this set of blue objects, which are representing a sample of rotation curves of galaxies. And these red lines here, again, a sample of sort of virial profiles of galaxy clusters. So as we're moving to larger objects, we're getting to lower and lower space-time curvatures on this y-axis. And then down the bottom here, we've got this sort of light blue line labeled P of K. That is representing the matter power spectrum, which we'll talk about a little bit later on in these lectures, but the spectrum of dark matter density fluctuations on cosmological scales. And there's also a line here called lambda, which shows you the kind of curvature you would associate to a cosmological constant. So what you see, oops, sorry, clicked the wrong button again. What you can see is that the sort of problem area of cosmology, where we need to come up with things like dark matter and a cosmological constant, perhaps to explain what we see, are really probing this very low curvature regime, the sort of bottom half of this plot. And our precision tests of gravity, things done in the solar system, in the laboratory, all live in the top half of this plot, a much higher curvature regime. We don't have such precision tests down in this low curvature regime. And that's kind of why we are allowed to explore this idea of deviations from general relativity, as long as they only affect these kinds of regimes. And again, we'll see a bit tomorrow some ways that have been developed of kind of changing cosmological gravity without messing up the solar system. Okay, so given that we are allowed, we're kind of okay to explore this idea of moving away from general relativity, there's a really nice theorem which acts as a starting point for doing this. And it goes by the name of Lovelock's theorem. I'm going to read this out and then we'll talk through, what bits of jargon mean. So Lovelock's theorem says that the only second order local gravitational field equations that you can derive from an action containing only the four-dimensional metric tensor of space-time are the Einstein field equations with a possible cosmological constant term. So what Lovelock's theorem is doing is kind of enumerating all the assumptions that make GR inevitable as the theory of gravity. And therefore, if you want to, and I should say, sorry, this is a mathematical proof. We're not going to go through the mathematics of it today, but I mean, GR is inevitable mathematically under these assumptions. So if we want to build a gravity theory that is not general relativity, we have to break some of these assumptions that are in the theorem. And there's kind of 4.5 options here. So option number 1 is that we add new fundamental fields to the universe. So you'll notice Lovelock's theorem says that the action for gravity is built only from the metric tensor of space-time, that object you would have met in a general relativity course, often written G mu nu. But if we build an action for gravity that contains new fields, like a new scalar field, somehow kind of mixed in with that metric tensor, we can get away from general relativity. Option number 2. Lovelock's theorem specifically applies to four-dimensional theories of gravity. So our usual four-dimensional metric in GR, 3 dimensions of space, 1 of time. So if we go to higher dimensions, we can build a theory that is not general relativity, and we can then ask what is the kind of four-dimensional limit of that theory. Now, there's a rather technical option here. Lovelock's theorem says that the field equations we're seeking are second order. That means they contain at most a second order time derivative. And that's usually a sort of solid restriction because second order field equations will be stable. If you go to higher order field equations, there is this generic possibility that your theory could be unstable. That means it could have the possibility of sort of negative energy modes that would run away to kind of plus or minus infinity. Generally bad news for your theory. However, if you're clever and you can build a theory that is higher order and stable, you can get away from general relativity. Option number 4 is non-locality. So there's this statement here that the gravitational field equations are local. That means what happens at a point in space-time only depends on other quantities at that point in space-time. What's happening here in Portsmouth can't depend on what's happening instantaneously, at least, over in the room with you in Michigan. However, if we can build gravity theories or allow gravity theories that have non-local behavior, then technically we can get away from GR, though that's a pretty exotic option. And finally, the kind of half an option, so I say 4 options, but I actually give 5 because I kind of won't go into this one today, is to give up altogether on deriving gravity from a fundamental action principle. Okay, so the way I think about this is, what if gravity is actually an emergent phenomenon? So there's some microscopic theory of space-time that we don't know about yet, and general relativity is kind of what emerges as the average property of gravity, a bit like doing sort of thermodynamics over some microscopic degrees of freedom. So again, then you can get away from GR. I'm not really going to go into that option today because that just requires a lot of apparatus and setup. Okay, so we can use these options to build a kind of map of this modified gravity landscape, if you like. So here it is. This is another plot that I made some years ago, where I was trying to kind of make a family tree of all the modified gravity theories that were appearing on arXiv at the time. And so I've used those 5 ways of breaking Lovelock's theorem in red here. And everything written around them in black is the name of a particular modified gravity theory. Now, don't have to worry about all these names today. In some sense, this plot is kind of designed to be a bit overwhelming. That's sort of the point. So you see there's a lot of possibilities, but perhaps you can notice that there's the most sort of activity down here in the sort of bottom sector of the plot, where it says new degrees of freedom. That's a fancy way of saying new fields. And I've divided that into scalar, vector, and tensor fields. So that's by far the most explored way to change the theories of change the laws of gravity. So what we're going to do now is I am going to walk you through 4 examples of modified gravity models, trying to draw where I can from different regions of this plot to give you a flavor of what's going on here. Okay, so these are the modified gravity models you need to know about. They are sort of historically the ones that have sort of shaped the field. However, what we're going to do is I'm going to show you the actions of these models. That's the way we sort of write down a model, is by writing down the Lagrangian. And so I'm going to do just a quick reminder first, or a very lightning introduction for those who haven't seen it, on how we write down a Lagrangian and how we get field equations from a Lagrangian. And I'll do that with general relativity to start with. Also, tiny little bit of notation we're going to need going forwards. The Planck mass squared, one of kind of the fundamental constants of nature, is equal to 1/8 pi times Newton's constant. That's often going to be important when I write things like the Friedmann equation. I will sometimes write it in this kind of form because from a sort of particle physics perspective, that's how we would write things down with the mass scale in. If you look at this and you're thinking, where's the 8 pi g that you might be expecting to see? It's of course, it is there. It's just using this relation. Okay, so a sort of reminder or lightning introduction to actions and field equations. So an action is the fundamental kernel of a gravity theory. It's, well, of lots of theories of physics. I like to think of it as sort of the magic seed, the magic bean from which you can pull out, if you know how to, all of the rest of the theory's predictions and properties. And so this is the action for general relativity with a cosmological constant. So it is an integral over 4 space-time dimensions. That's why there's this d to the 4x here. And there's this volume element that contains minus the trace of the determinant of the metric tensor of space-time. That is just there so that volume element transforms correctly. So basically, don't worry about it. The real kind of meat of this action, the important part, is this object R, which is the Ricci scalar, which hopefully everyone met at some point during a general relativity course. And you might remember it's built out of second derivatives of the metric contracted in a particular way. Notice that the Ricci scalar is multiplied by the Planck mass squared over 2, right? So that's the important constant we saw a moment ago. Here is the cosmological constant, right? Literally sitting in the action, lambda. Then I'm going to be slightly hand wavy when it comes to matter. I do want to describe a universe that has general relativity and matter fields in it, dark matter, baryons, etc. I don't really want to get into the matter sector today, so I will just sort of leave this as there are matter fields sitting here. So this is what we write down. Now, what we want to do is derive the equations that govern this theory. And to do that, there are a couple of routes, but the sort of route that I will follow today is that we demand that this object, the action, is invariant under small changes in its field content. And in this case, there's really only one field to worry about, because I said I'm not going to worry about matter fields. There's only one other field involved, which is the metric tensor G mu nu. And so we demand that we can make a small change to that metric tensor, so introduce some perturbation delta G mu nu, and this action should not change. It should remain invariant. So I'm going to do that. I'm going to plug in this transformation in green into the action above. I'm not going to go through all the sort of steps of algebra, but it's done in lots of places, including these lecture notes by David Tong. Okay, and here we go. Here's what happens. So we're now looking at the change, the perturbation to this action. And what does it contain? We've still got our volume element here. We've still got our mass scale sitting here. But now inside this round brackets, we've got a combination of objects built out of the metric. Some of you might start to recognize this as components of the Einstein tensor. And that's all multiplying a perturbation delta G mu nu. And what's happened is we've also used a definition that the sort of small change to the matter action when we vary the metric introduces this object T mu nu, which is the stress energy tensor. So what I'm going to do now is I'm going to collect together these two terms. So this bit with delta G mu nu, this bit with delta G mu nu. Put those two together. And remember, we said the action is invariant, so this small change all has to vanish. And the only way that can happen in general is if the contents of the round brackets vanish. So we set those round brackets equal to 0. And that, of course, gives us the Einstein field equations. Right? All we have to do is substitute in the fact that the Planck mass is inversely related to Newton's constant, and hopefully this is something everyone recognizes from a general relativity lecture. So on the left-hand side, these first two terms would be the Einstein tensor. Here's the cosmological constant. And on the right-hand side, the stress energy tensor containing implicitly dark matter, baryons, radiation, etc. Okay, so that is the procedure. Now what we're going to do is we're going to write down some more exotic, funky actions for theories of gravity that start to deviate from plain old general relativity. And whilst I won't take you through every step of the maths, the procedure for getting the field equations for those theories would be exactly the same. You just have to vary the fields that sit in the action and set that variation to 0. So here we go. Let's get started. Our first stop is a theory called quintessence. So what we've got, let's have a look. We've got our volume element as before. We've still got a part that looks like the Ricci scalar multiplying the Planck mass. So that hasn't changed from general relativity. But we've now got this extra scalar field phi sitting in the universe. And it's got two contributions. It's got a kinetic term, so nabla phi, and it's got a potential, which we'll just write as U for now. So we've added a scalar field to our universe, but we haven't actually changed the part of the action that describes gravity. It's still the same as it was in general relativity. So quintessence, at least in my vocabulary, is a dark energy model, because it adds this new field, which can do kind of exotic stuff, but it's not really changed what gravity is. Okay, so this is my distinction between modified gravity and dark energy. So just as some examples, here are two quick examples that I pulled up from the literature of particular potentials that people have studied in quintessence models. So there's a kind of one here with a cosine that comes from axion physics. There's an inverse power law. You can plug in like particular forms for you here that will do interesting things, and you can study the theory. We're going to move on from quintessence because I want to get to a proper modified gravity theory. Okay, so I'm going to make a couple more changes to this action. So watch the action closely. Here we go. Okay, so stuff is starting to get a little bit more complicated. Now our gravity piece, where before we just had the Ricci scalar, it's now got this function of a scalar field, f of phi, sitting in it. We've still got the kinetic term that we had before, but now it's got this kind of prefactor which contains another function of the scalar field. Sorry, I should have said this one is sometimes called the conformal coupling. And we've got the potential as before. So there are three functions appearing here, f, omega, and u. And this is a genuine modified gravity theory because now we've changed that Ricci scalar term. Now, one of the tricks you can play with a scalar field is you can always redefine a scalar field. And actually, we can redefine our scalar field such as to get rid of one of these three functions. So I could introduce a new scalar field, I'll call it phi tilde, which is equal to f of phi. And then I can just push this definition through the rest of the action. Now, I'm going to be a bit lazy in doing that today. So I'm going to change f of phi for phi tilde, but then I'm immediately kind of going to drop all my tildes just to kind of keep the notation clean. Okay, so here we go. All I've done is I've replaced that by phi here. I haven't bothered to kind of show the change propagating through all these other terms. But now we have a genuine modified gravity theory, and this is something we would call a scalar tensor theory because it's got the tensor, the metric tensor of general relativity, but it's got this new scalar field in it as well. Now, there's a particular subcase of this modified gravity model that was studied historically. So one of the first modified gravity models ever written down was a subcase where we set this potential u to 0. And we take this function omega, we take that to be a constant. And that's a theory called Jordan-Brans-Dicke theory, which was written down in the 1960s. So let's make those changes. Right, so here's Jordan-Browns-Dickey gravity. I've just got rid of the potential, just made omega a number, a constant. And how you get from this theory back to general relativity is by sending that constant omega to infinity. And that might not be completely obvious. I'll explain that a bit more in a moment. But if we just accept that for now, the experiments that have been carried out in the solar system, so sending pulses of radio waves across the solar system, measuring kind of how they get delayed as they travel through the gravitational field of the sun. Those kind of experiments have allowed us to yield bounds, at least on solar system scales, on that parameter omega. And the constraints are that omega has to be greater than 40,000. Okay, so you can't really constrain omega all the way up to infinity, but like the higher and higher we push it with the data, basically the more and more constrained this theory is. Let me just explain why omega going to infinity is the sort of limit of this theory. And then to do that, we're going to take our first look at modified gravitational field equations. So remember we said to obtain the field equations, we make these small changes to the field in the action. So the metric changes as before, but now we've got an extra field present. We've got this scalar field. So that's also going to have a small change made to it. And we'll actually get an additional equation because we have to demand invariance under this perturbation as well as this perturbation. So again, skipping the algebra, but going to the results. Here you go. Here is your first modified gravity field equation. It's pretty big, right? Stuff gets very big very quickly in these theories. So you can see we've got the usual parts here. We've got the Einstein tensor on the left. We've got the stress energy tensor on the right. And then we've got all these other new terms. What you can also see is that we've got something going on here whereby our gravitational coupling constant has been renormalized by the value of the scalar field. So we've got this effective gravitational constant, which now potentially can change with time. If, for example, the scalar field evolves over the universe's history, and it will do, the strength of gravity changes with time. So already we're starting to change the physics. I said we also have to vary with respect to the scalar field. And so when we do that, we get an additional equation that tells us that the scalar field, so box phi, second derivative of the scalar field, so this is like a wave equation on the left, is sourced by the trace of the stress energy tensor. So radiation, for example, won't contribute, but if we have some matter source, so dark matter or some baryons, that will source the scalar field. Now we said the GR limit here is obtained by sending omega to infinity. Plus the normal stress energy conservation. So if we send omega to infinity, we kill off that right-hand side. And also what we have to do actually to get general relativity back is set phi to a constant. And if phi is a constant, all of these derivative terms here vanish. This phi here just becomes a constant renormalization of the gravitational coupling strength, and we're basically back to general relativity. Okay, that was your modified gravity model number 1. What I'm going to do is I'm going to squeeze in quickly a modified gravity model number 2 before we have a break. And modified gravity model number 2 is one of the biggest ones, one you might have heard of, is still talked about a lot in the research literature. And it goes by the name of F of R gravity. So just to explain this, I've brought back the action we had for general relativity. This time I haven't put in a cosmological constant. So it was just contained this Ricci scalar R. But it's very obvious to ask, why does this have to be linear in the Ricci scalar? Why couldn't we have some more general function of the Ricci scalar f, and hence you get to the name F of R gravity. Now let me show you something. I'll say that the F of R gravity is intrinsically a higher order theory. So remember when we spoke about Lovelock's theorem, we said we could have field equations with more than second order time derivatives, but that would make a theory very often unstable. But let's look at something with f of r gravity. I'm going to write down for you an equivalent action to the one up here. So here it is. Looks a bit more complicated, but it's actually not. So this term f of r has just gone down here. And I've introduced these two other terms, but they're completely the same. So they cancel each other out. I've sort of just added a term and taken it away again. And this object f with a subscript r is just the derivative of this function f with respect to its argument r. Okay, why have I done that? Doesn't seem to do much. Now let's consider that this object f sub r, let's treat that as a scalar field. Then what happens is we start to have something that looks like scalar tensor gravity that we had before. We've got some conformal coupling modifying the Einstein-Hilbert term. And we've got some other object here that we can identify as the potential for our scalar field. And so what actually happens is that f-bar gravity looks like a scalar tensor theory, but without the kinetic term. That was the part that was parameterized by a function omega. Okay, so just rewriting that, f of r gravity is actually a scalar tensor theory in disguise. It can be mapped on to a scalar tensor action. And that's why, even though f of r gravity looks like it should be higher order and potentially unstable if you sort of write out the field equations, it is actually stable under the hood because it's really just a scalar tensor theory with clothes on. Okay, the last thing I will do before the break is just show you, oh yes, sorry, this is just me showing you that f of r gravity lives up here, but we can actually map it to a scalar theory. I've just put on the slide here some examples for the functional form of this object f of r, just so it doesn't remain completely mysterious. Here are 4 examples that have been used in the literature. I think they come from this paper up here. And they look kind of weird and strange. There's lots of strange forms like tangents and power laws and things. But if you take the appropriate limit of these functional forms in the high curvature limit, so where the Ricci scalar r is much greater than some value rc, they all reduce to the form up here. So r minus mu and rc, where mu and rc are just constants of the theory. So all of these theories are designed to basically reduce to GR with a cosmological constant in the high curvature limit. And so they're designed to kind of mimic lambda CDM in certain environments and hence maintain consistency with those small scale tests of gravity. Okay, according to my timer, that is 41 minutes. So I think we are at a break point. I'll let a chair step in here, and I guess we start a timer for 10 minutes and then we come back. Is that the plan?
Yes, Tessa, thank you. We are at the break, not quite breaking point. We are at the break point. Yeah, thank you. Perfect timing. We can take 10-minute break. We are back in a few minutes. So let's do that.
Okay, I'll be back.